We're given a function that is defined only graphically. And then from that function, or based on that function, we're going to create a series of related functions and then ask to perform certain operations on them so that we really understand how the various functions relate to each other. In particular, we're going to be needing both flavors of the fundamental theorem of calculus. We'll need to demonstrate our understanding of concavity as well as increasing and decreasing values of functions. And we'll have to use the quotient rule and the chain rule in a purely symbolic way. So let's just jump in. Part A, this will be fun. It's a good exercise. Part A asks us to find g of 3. Now g itself is defined in terms of the integral of f of t dt from some constant value up to x. So this requires us to use the integral form of the fundamental theorem. So we know that g of 3 equals g at some lower known point. We're going to pick negative 3 for reasons I'll clarify in a moment, plus the integral from negative 3 up to 3 of g prime. I could have written that with a dx, but the dt is just as easy, and since it's a dummy variable, it doesn't really matter. Okay, now, why did we pick g of negative 3? Well, because g being defined in terms of an integral, if the start point and the stop point are identical, then we know the value of the integral at that point regardless of any understanding about the integrand. Namely, we know that this is 0. We also know that g prime of t is, in fact, f of t. So this g prime really is f of t. Again, that's inherent in the definition. So we're going to graphically evaluate how much signed area there is as we progress from left to right, beginning at negative 3 and continuing to 3, which would be right here. Okay. So let's see. We've got g of 3. I think I want to switch back to black on that. We've got g of 3 is 0 plus, now how do we find this signed area? We're going to go from negative 3 to 2, and that will incorporate the area of this region here, this triangle. So the area of a triangle is 1/2 base times height. So that's 1/2. We have a base of 1, 2, 3, 4, 5. 1/2 times 5. And what is our height? 1, 2, 3, 4. That covers that area. Now we have to add in this area. And remember, we've been saying area, but originally we said signed area. And that's important here because this is going to constitute negative signed area. Again, this triangle goes right up to here. And what do we have? We have 1/2, a base of 1, and a height of negative 2. That's how we introduce the signed nature of the area. So we could leave it at that, but tempting fate, I'm going to write this as 10 minus 1 equals 9. That's our answer to A. What does B ask for? We need to find the open intervals between negative 5 and 4 where g is increasing as well as concave down. Let's start with g increasing. g of x increasing is simply another way of saying that g prime of x is greater than 0. And in this situation, because of the fundamental theorem, the definition of g prime's derivative, we know that that is f. So what we're really saying is that f of x is greater than 0. Those are the regions we're looking for. Okay, so where does that occur? This occurs when, all right, where is f greater than 0? From -5 to 2. When that inequality is satisfied. Okay. Now, what about g concave down? Well, concave down, again using our little cheat sheet here, concave down means the second derivative is less than 0. So that's equivalent to g double prime of x being less than 0, which in turn, because of the specific definition we have for g in this case, it means that f prime of x is less than 0. Now, where does that occur? This occurs when, let's see, what do we want? Negative. We want the derivative of f to be negative. And the derivative corresponds here to the various slopes of these line segments. So here's one place where we have a negative f prime, and here's another region where we have a negative f prime. So what do we have? -5 to -3. We have a negative slope. And 0 to 4. Okay, so what we want is the intervals where this and this are simultaneously satisfied. So let's continue B up here. And I'm just going to put a line down to separate out. So these conditions are satisfied when, let's say they're satisfied over x -5 to -3 and what is that, x 0 to 2. That handles B. C, we have a new function, h, and it's defined in terms of g of x, which itself is defined in terms of f of x. So we use the quotient rule to find h prime of 3. To determine h prime of 3, namely h prime of 3 equals the bottom 5x times the derivative of the top g prime of x minus the top function, the function in the numerator, times the derivative of the denominator, which I'm just going to write as 5. And that's all over the square of the denominator. Then this whole thing is going to be evaluated at x equals 3. Well, what sort of sense can we make of this? Let's see. I'm going to write this as h prime of 3 equals 5 times, what is x? 3. Now, what about g prime of x? Well, g prime of x is f of x. So let's just note that. And what is f of 3? Well, let's see. F of 3 is -2. Just reading it off from the graph right here. That is f of 3. So we have that. And then we have to subtract g of x. So what do we need? G of 3. Well, how convenient that we already found g of 3 to be 9 times 5. And all over 15 squared. Well, what have we got? 15 times -2, -30, minus 45 is -75 over 225, and that is -1 over 3, because 75 goes into 225 3 times. Okay. Although, truth be told, when I did this under timed conditions, just like the exam students, I just left it in this form. Didn't have time to simplify. And apparently you don't lose any credit for doing that. Okay, new function, again defined in terms of x, or rather in terms of this graphical function f. We have p of x equal to f of x squared minus x. What will they think of next? Okay, so we need to find the slope of the tangent line to the graph of p where x is -1. Or in other words, we need to find p prime of -1. Well, p prime of -1 then is simply the derivative with respect to x of f of x squared minus x, that whole thing evaluated at x equals -1. So here's where the chain rule comes in, because we can't directly take the derivative of f with respect to x, since f itself is in turn defined in terms of x squared minus x. So we write p prime of -1 using the chain rule. This expression can be rewritten as follows. The derivative of f with respect to x squared minus f of x squared minus x, we can take its derivative with respect to x squared minus x. That we know how to do. And now we'll have to, in turn, take the derivative of x squared minus x with respect to x. Well, what do we know about these? What's the derivative of x squared minus x with respect to x? 2x minus 1. That was easy. Now what about this? This is just f prime. Oh, I should add, all of this we're going to evaluate at x equals -1. I'm just carrying forward what we said on the previous line. Okay. So when x is -1, this is 1 minus -1. This is 2. So what this expression really is asking for is f prime of, did I get that right? F prime of 2. Well, what's f prime? It's the slope as we go from here to here. Let's see, what are we doing? We're at 4, 0, comma 4. So we're going down 8 and over 4. That's a slope of negative 2. So f prime of 2 is negative 2. And 2 times negative 1 minus 1 is negative 3. Put it all together, and we get that p prime of negative 1 equals 6. Isn't that chain rule cool?